All right, in chapter 4, we're going to start off by talking about related rates. Okay, so first off, what is a related rate? A related rate is when two things are, as it says, related to each other, and how the rate of one thing changes as the second changes. Now, that doesn't make sense. And I was actually going to have a balloon for you guys to blow up and deflate, but of course, I'm a horrible planner. I don't have that. So instead, what I'm going to show you is a quick YouTube video. And as I'm showing you the video, what I want you to do is I want you to pay attention to um, the relationship between the radius and the volume of the balloon. So as the radius of the balloon decreases, what is happening to the volume? All right, let's watch this super quickly. All right, so notice that in the beginning, the volume was decreasing slowly as the air was slowly coming out, and as a result of it, the radius was also decreasing slowly. But then later on, at the end, as the so here the volume is decreasing slowly, and so is the radius. But at the end, both the volume and radius they decrease very quickly, and those are related, right? Like as the rate of the volume increases in the deflation, the rate of the radius decreasing is also growing. So that's like the essence of related rates. How are two things related? Now here we have a bunch of steps to go through, and I'll go through the steps with you. The picture is optional. I think it helps, but it's if you don't, that's okay. The formulas I think are more important. So step one, draw a picture and two diagrams. Identify the given information, identify what you're looking for, write an equation that relates to two variables. So this is going to be important. Write an equation that relates to two variables. And then step 5 is always going to be the same. We take the derivative of both sides, because when you talk about related rates and how rates are changing, the derivative measures how fast or slow something is changing. So we take the derivative of both sides of the equation with respect to time, and then substitute and solve. So let's take an example, because none of this is going to make sense until we see an example. So you have a spherical snowball that is melting in such a way that its radius is decreasing at a rate of 0.4 centimeters per minute. At what rate is the volume of the snowball decreasing when the radius is 9 centimeters? So as we saw in the balloon, um, as the volume decreases, so does the radius, and the rate at which the volume decreases is related to the rate at which the radius decreases. So what we want to know is, in this case for the snowball, when the radius is 9 centimeters, at what rate is the volume of the snowball decreasing? So first off, we need a formula, right? So the formula for volume, now why do I use this formula? Because we want to know at what rate is the volume of the snowball decreasing. So because I'm relating volume to radius, we need to find a formula that's going to relate the volume to the radius. And that formula is going to be volume equals to 4/3 pi r cubed. Now, all the formulas you need for the homework and for the exam are going to be in these notes. So I recommend this is what you refer to when you're stuck on something. So the volume and the radius are related by the formula. Volume equals to 4/3 pi r cubed for a sphere. Okay, now here's what we know. We know that the radius is 9 centimeters, because that's the point at which we're concerned with. And we also know that the radius is decreasing at a rate of 0.4 centimeters per minute. So dr dt, is the change of the radius with respect to time. It's going to be 0.4 centimeters per minute. So we need two diagrams. We need one diagram for the actual radius, and then one diagram for the rate of change. Now again, if you don't do this, if you can do it without the diagram, that's perfectly fine. But this is just to give you guys a visual for those of you that can be helped by it. All right, so we have the relevant information. The radius is 9 centimeters. The rate of change of the radius is 0.4 centimeters per minute. And what are we looking for? So the question is, at what rate is the volume decreasing? So the rate of change of the volume is given by dv dt. So how fast is the volume changing with respect to time? Okay, dv is the rate of change of the volume, over dt is the time. So our formula is volume equals to 4/3 pi r cubed. I'm going to take the derivative of both sides with respect to time. And remember that when you have a v variable with a t input, um, we're gonna get that dv dt, right? So we have dv dt equals to 4/3 pi times. Now, so 4/3 pi is a constant, so it's going to remain the way it is. Now for the r cubed, so here I'm going to write the derivative with respect to time of r cubed. And then if you just differentiate this, we get a 3r squared, but we have an r term with respect to time, and so we're going to get a dr dt. All right, so we have that. That's where the 3r squared dr dt comes from when we differentiate the r cubed. And now, what are we looking for? I'm looking for the rate of change of the volume with respect to time. So I'm looking for dv dt. And on the right side, I know what my radius is. My radius is 9 centimeters. dr dt is a rate of change of the radius, which is 0.4 centimeters per minute. So I plug that in. Well, first I'm going to simplify this by canceling out the 3. So I get 4 pi r squared dr dt. And then so I'm going to replace the radius with 9, replace the dr dt. That's, again, dr represents the rate of change of the radius over time. That's what dr dt is, which is 0.4 centimeters per minute. So anytime you're talking about decreasing or increasing a rate, that is going to be your dr dt or whatever, whatever the rate of change is. And then I just simplify that, and I get 407.15 centimeters cubed per minute. So it means that when the radius is 9 centimeters, the volume is decreasing at a rate of 407.15 cubic centimeters per minute. Okay, once again, please come to class prepared with any questions you may have about this. Let's take the next example. The altitude of a triangle is increasing at a rate of 2 centimeters per minute. What is the area of the triangle? While the area of the triangle is increasing at a rate of 3 square centimeters per minute. So now we have two different rates of change. One for the altitude and one for the area of the triangle. At what rate is the base of the triangle changing when the altitude is 11.5 centimeters and the area is 100 square centimeters? So first, let's take a look at what are we looking for. Okay, we're looking for the rate of change of the base of the triangle, right here. At what rate is the base of the triangle changing? So we need a formula that's going to relate the area to the base. And the formula for the area of a triangle is 1/2 base times height. Now on the side, I put all the information that I have. The altitude is the same thing as the height. So dh dt, in other words, the rate of change of the height with respect to time is 2 centimeters per minute. We also know the area is changing at a rate of 3 square centimeters per minute. So dA dt is going to be 3 square centimeters per minute. That's the rate of change of the area with respect to time. Our height is 11.5 centimeters and our area is 100 centimeters squared. What am I looking for? I'm looking for dB dt. At what rate is the base of the triangle changing? So what I recommend is that you write down all this information before you start the problem. That way it's all there. All right, now, once we have a formula, we can, and again, if you want to have the illustrations, you can. The height is 11.5, this is altitude. The area of the triangle is 100. dH dt, so the rate of change of the altitude is 2, and then dA dt, rate of change of area, is going to be 3. We're looking for the rate of change of the base. So now let's differentiate everything with respect to time. And because we have two terms, we're going to have the product rule. Anytime you multiply two terms, we have the product rule. So our first term m is going to be 1/2 b, and our second term n is going to be h. So on the side, I wrote down m is 1/2 b, and so m prime is going to be 1/2 dB dt. Now, why do I get a dB dt? Because I have a b variable with respect to time. So m prime is going to be dB dt times 1/2. 1/2 is a constant. Our n is going to be h, and our n prime is going to be dH dt, because again, I have an h term with a t input, so I get that dH dt. This is from chapter 3. And then I plug it in. So I take both sides with respect to time. So here I just get a dA dt. Now on the other side, I'm going to get my product rule. Okay, so my product rule is going to be n times m prime. So it's going to be h times 1 half dB dt, which is my m prime, plus m, which is 1 half b, times n prime, which is dh dt. So if I plug everything in, my dA dt from here is equal to 3. My h is equal to 11.5. My dB dt, that's what I'm looking for, so I'm going to leave that as a variable. Then I have 1 half, that's a constant. My base is missing. I don't know what my base is, right? They give me height, they give me area, but I have no idea what my base is. And my dH dt is equal to 2 from right there. Now I have a problem because I need to solve for dB dt, but I can't do that unless I know what my base is. So how do I solve for base? Well, luckily we have area and we have our height. Our area is 100 and our height is 11.5. So from there I can solve for my base from the original formula. So if my area is 1 half base times height, my area is 100, my height is 11.5, I can solve this equation. 1 half times 11.5 is 5.75. And then if I divide both sides by 5.75, it's going to give me 17.3913043. Now in any kind of a middle step, you need to keep at least 6 to 7 decimal places. Okay, keep at least 6 to 7 decimals, because if you don't, you're going to get a rounding error. You round at the end, but never in any kind of a middle step. So I replace my b with, well, the 1 I have and 2, they cancel out. My b is 17.3913043 from here. And then I just solve that equation. So I subtract both sides by 17.3913043, and then I divide both sides by 5.75 because 11.5 times a half is 5.75, and I get my dBdt to be negative 2.503 centimeters per minute. Okay, now what does that tell me? It means that my base is changing at a rate of negative 2.503 centimeters per minute when the altitude is 11.5 centimeters and the area is 100 square centimeters. So the main thing here is to start with the formula, take the derivative with respect to time of both sides, and then just plug in all the information you have. That's it. Here's the next example. A gravel is being dumped from a conveyor belt at a rate of 20 cubic centimeters per minute. Okay, now because the gravel is being dumped, this is going to be the rate of change of the volume, because that's like how fast the hole is filling up. It forms a pile in the shape of a right circular cone whose base diameter and height are always equal. How fast is the height of the pile increasing when the pile is 12 feet high? Okay, so first let's start with the formula. The volume is equal to 1/3 pi r squared h. Okay, this is going to be the volume of a circular cone, and we're given that. That's how we know to use this volume. And again, you will know these formulas because they'll be in your notes. So now what we're going to do is we're going to write down all the information we have. We have our volume, dB dt is 20 cubic feet per minute. That's how fast the gravel is being dumped. So the volume is changing at this rate. Now here's what we know. We know that how fast is a pile increasing when the pile is 12 feet high. Okay. And we're also told that the diameter and the height are always equal. So the diameter is equal to the height. Now the diameter, if you recall, is equal to 2 times the radius. And why do I need the radius? Because our formula has a radius in it, not the diameter. So I'm going to rewrite the diameter as 2r, so I can say 2r is equal to h. What am I looking for? How fast is the height of the pile increasing? So the rate of the change of height is going to be dH dt. That's what I'm looking for. So when the height is 12 feet high, how fast is dH dt? Now, the rest of the problem I'm going to have to finish in the next video because I only get 15 minutes and my 15 minutes are almost up. But I will continue the video in the problem in the next video.